Good morning. Welcome to Friday morning. Thank you for coming. First of all, a couple of introductions. For those that don't know, my name's Alex Benet. I'm a virtualization engineer at Linaro. I mostly work on QEMU's TCG engine, which is its emulation side, but I have been known to touch KVM from time to time. And you can find me on the Linaro channels on IRC as AJB Linaro and on the QEMU channel as ST Squad. So you'll have been hard-pressed not to have heard of Docker over the last 5 years. This data is from Google Trends. It kind of gives an indication of the searchability of particular terms. So virtual machine is self-explanatory. Vagrant is a tool that's used to provision virtual machines in a similar way to Docker. And Ansible is also quite a popular tool for deploying virtual machines as well as real hardware. But as you can see, over the last 5 years, Docker has really beaten everyone on the hype train. There's a couple of reasons for that. It's very developer friendly, so it's pretty lightweight. You can run a lot of Docker containers on your machine compared to virtual machines. The tooling is very much developed to encourage agile development methodologies. So it encourages rapid iteration, turning around and trying lots of different images. It also has quite a good DevOps story. So a developer can go from testing something on their local machine to pushing something into the cloud very, very quickly. And then in the cloud, you have lots of cloud orchestration services. So you're thinking things like Docker Cloud, Kubernetes, and pretty much all of the public cloud providers have their own branded orchestration stuff for deploying containers into the cloud. But Docker's not really the only use of containers. There are other use cases. Two ones that come to mind. Application sandboxes. So this is getting more popular in the Linux world, where you want to distribute an application that's rapidly updated, or you want to distribute it from outside of the distro. And these tend to be done in packages that use containerization technology. So we're talking about things like Snap and AppImage. And you bundle together your application with the libraries you need, and then when it's run, it's relatively isolated from the rest of the system. Another popular use case is Android in a box. There's actually a project called Ambox that does this. And this is for supporting, for example, if you're running an alternative phone operating system and you want to run Android apps alongside your system, rather than polluting your rootfs with Android, you can put Android in its own little container. And actually, this is the approach that CHROMOS uses to deliver Android apps. So containers are getting pretty ubiquitous on the IT landscape. So let's just have a quick review of what containers are. So really, a container is just a bunch of processes that run on a system that are contained in some arbitrary way, and they have a degree of isolation from the rest of the system. So here we have a host system with its compute, storage, and I/O running a host kernel. The green ones on the left are just normal user space processes, and the ones in the little dotted boxes are contained somehow. But from the kernel point of view, containers are just leveraging a bunch of existing technologies. So the first one that's usually mentioned is namespaces. So a namespace is just a view of a particular aspect of the system that a particular group of processes see. So in this example, we've got the PID namespace. You can see on the left-hand side, we've got the normal init and usual things that you run on a Linux system. But inside the namespace, you can have your own PID1 and other PIDs. There's no clash between that and the host. They have different real PIDs, but as far as those processes in the container are concerned, the only processes, the blue processes, can see other blue processes. And the same for the other container. So there's a number of namespaces. There's a mount namespace, which affects how you see the file system, a net namespace for accessing networking resources, and a user namespace for access to things like user IDs. Another key technology is control groups. So control groups, again, act on a group of processes and allow you to do accounting on what those processes are doing. And then you can set limits. So you can limit things like the amount of CPU time they'll use, the amount of network and disk I/O that they can use, and you can then group them and set the sort of priority that they have access to resources on the system. And finally, you can control a group of processes as a whole. So for example, systemd uses control groups when it wants to shut down a unit and it wants to get all the child processes that something might have started. The next thing is sandboxing. So sandboxing is limiting what sort of services a process can access on the kernel. So there are two main ones here. setcomp, which limits the sort of system calls that a process can make, and netfilter, which is limits what sort of network connections and what sort of ports you can access. Both of these increasingly use BPF to actually do the implementation. And finally, there's file systems. So the way containers treat file systems is usually quite a big part of it. So in a typical use case, you might have a hub or registry sat on the internet which has pre-built images. They might be distributions, they might be pre-built application images running in a preferred distro. And then when you want to build your container, you pull one of these off the internet, you add a couple of layers to the file system that maybe you add your own application or your own bit of configuration. And then finally, when you run the container runtime tends to create an ephemeral layer of the file system. So when the thing is running, any stuff that it dumps onto the disk will get thrown away when the container's done. These things tend to live for a relatively short time. But this is important because it means each time you instantiate a new container from an image, it should behave the same way because it hasn't accreted any crap. This uses existing file system technologies, so you've got file systems like AUFS and overlay, although with modern file systems like ZFS and ButterFS, this tends to be more heavily integrated into the file system itself. And finally, you have the container runtime. So the runtime is what's responsible for setting up the sandboxing and the containerization of the group of processes. So everyone's heard of Docker, but Docker is actually predated by about 4 years by LXC. And there are other examples. Probably a surprise to no one, systemd has its own way of launching a group of containerized processes called systemd nspawn. But there is a problem with containers. So this is a CVE from earlier this year. As you can see, a container with an attacker-controlled image, which usually means you've downloaded something from the internet and not vetted it properly, is able to escape the container and overwrite the runC binary, which was the binary that launches the container, on the host. And once you've done that, you've got root access on the host. Now, I'm not going to go through all the details of this, but suffice it to say, what the attack was able to do was it was able to use a bypass through the proc file system. It modified a binary that you were going to run in the container. When it tried to run the binary, it ended up running itself, and an attacker process could just watch for that to happen, open a file descriptor, and write to the host binary. But the point about this is that the kernel feature space is very, very large, and it only takes one failure in containership to get through that and own your host. So, let's talk about VMS. Sorry, let's talk about VMs. So, what is a virtual machine? Well, the clue's in the name. It's a machine, but it only exists virtually. So what we have here, we have our normal user space processes, but in each of the virtual machines, you're modeling a bunch of hardware, you're running a guest kernel on the machine, and they're running their own user space tasks. Now, from the host point of view, it just appears as one more user space task, but from the guest, all they see is the internals of their own machine. And it provides a different sort of isolation. So in this example, on the left we have our guest. So a user space application on the, wants to write something to the disk. It makes a system call into the guest kernel. That goes through the guest kernel's VFS, file system block, eventually comes out into the driver, and it writes something to the virtual disk. This is the point we do a VM exit. So we exit the virtual machine. We come into the host side, and KVM can do a number of things with that. Some hardware is VM aware, so you can pass that directly through. Otherwise, you might emulate the access directly inside the host kernel, or even pass it on to user space to do the emulation. And once user space has done its emulation, it might even do another system call into the host kernel this time to finally write something to the disk. So the isolation that VMs provide is basically on this barrier of the devices that you emulate. And that's a relatively contained task. So how can we get the best of both worlds here? Well, like with most things in computer science, you just add more layers. So here's an example of running containers in VMs. So we have our guest VMs. They have their hardware and a guest kernel. You have some sort of agent that you run inside the guest, and usually this is talking to the agent on the host. So they have some sort of mechanism of talking, so you can launch containers, and then you launch your containers in the VM. But all this abstraction does have a cost. So this is a little test case that I wrote. It's nothing clever. All it does is it takes the current uncompressed copy of the Linux kernel and compresses it with the PIG's compressor, which is a multi-threaded compressor. But you can see there's a little bit of stuff that happens on the left-hand side. All the various Docker daemons wake up. Eventually, run C, which is the task that's responsible for creating the container, gets involved. And you can see the PIG's task along at the bottom running. The whole thing takes about 10.9 seconds on my Synquacer. This is the same task running in a VM. You can see where the tarball gets loaded in about 2 seconds. I had to use a different tool to grab the grasp of this. This is a boot chart. So the container, the task that we're doing gets running at 2 seconds. The whole thing takes about 12 seconds to do. But actually, that's not a complete view, because that's the view from inside the guest. If I run the boot chart from the host, as soon as I kick off my task, you can actually see it takes a lot longer. You can see the same little peak where the tarball is read in. But there's about 2 seconds of boot time of the kernel that the in-guest chart doesn't catch. And then there's a number of seconds before that, which is the time it takes for CHROMU to get loaded and all the processes to get created so CHROMU can start running. So it actually takes more like 23 seconds. So obviously, just using VMs off the bat adds a fair bit of overhead. So we need to talk about the sort of mitigations that we can do. So there are a couple of classes. First of all, virtual hardware. If you want to be careful about the virtual hardware that you present to your guest, you want it to be minimal. Most default guest hardware try and emulate a whole machine. And you don't actually need that if all you're going to be running is a container workload. You want the hardware to be para-virtualizable. So instead of emulating a device and causing a VM exit every time you write, you want to use something like VirtIO. VirtIO is specifically designed for virtualization environments and tries to minimize the number of VM exits you have to do any particular thing on the system. Another thing that's useful is having hot pluggable hardware. That means you can boot up a guest image using relatively few resources and then hot plug resources into it when you actually want to do some workload. The next thing to consider is how you set up your guest. You want a minimal kernel. Most distro kernels do an awful lot of extra stuff that you don't really need if all you're going to do is run a container. Usually they have a bunch of modules enabled. They have to probe for hardware that they might not find. and a whole bunch of extra stuff which is useful if you're not sure of the hardware you're running on, but you can get rid of if you know exactly what you're going to run. You'll generally want a lightweight user space, because the user space in the guest is going to do very little apart from run the agent and get the container up and running, because the container will have its own user space in it. And then finally, direct boot or using some sort of micro BIOS. BIOS is great for abstraction, but again, if you know exactly what your hardware is, it's faster just to get the kernel loaded and get it running. The other thing you want to take care of is how the guest and host communicate with each other. So there's two technologies I want to talk about here. First of all is VirtIO VSoC. So this is a bidirectional socket. So on the guest side, it just appears as a device. You can open it just like a normal file device, write stuff, and you get a bidirectional communication with the host. This is zero configuration, so you don't need to worry about bringing up an Ethernet interface or getting an IP address or any of that stuff. You just open and go. So it's more efficient than using networking, and it's a good choice for communicating between guest and host agents. Another one which is upcoming is VirtIO FS. So most file systems that you use with virtual machines, if you want to talk outside of the virtual machine, tend to use some sort of networking file system. VirtIO FS takes advantage of the fact that you know you're co-located, the guest and the host are actually running on the same hardware. So VirtIO FS provides a POSIX API instead of a disk to the guest. And then you can use things like shared memory, so you can map a file into shared memory and access it straight away. So this reduces the number of exits you need to do to get files accessible to the guest. So having looked at the general mitigations, I'd just like to go through a couple of examples of where VMs and containers have been used together. So the first one I'm going to talk about is CHROMOS's CROSTINI. So for those of you that are not familiar with CHROMOS, CHROMOS is Google's Linux on the desktop solution. They have a fairly strong approach to security, so they have a trusted boot path that goes all the way from the firmware to the blob that they run in the browser. It's based on Linux, not that you'd know, and a very minimal gentle user space, because the main thing is it just wants to run the Chrome browser. Now they did have a developer mode that you could turn on these, and if you turned on the developer mode, you could install a Linux root FS and put it in a chroot, and you could get access to all your Linux tools. But in the process of doing that, you basically had to disable all the security features that made CHROMOS good. So they wanted to come up with something better. So this is the architecture they have. It's called CROSTINI. So they have a virtual machine runner called CrossVM. And then their guest kernel is a very lightweight kernel running LXD, so they're not using Docker here. And then the actual container itself runs, by default, it's a version of Debian Scratch, although you can run other operating systems. And then you have agents running in the guest container that allow it to talk to CHROMOS. So these deal with things like making copy and paste work between the guest and CHROMOS and be able to launch URLs, that sort of thing. The most interesting thing about this architecture is CrossVM. So CrossVM is written in Rust, so it's a memory-safe language that they've used to do the implementation, because they're favoring security over performance. They've gone for a multi-process approach, so each bit of device emulation is done its own separate process, so it's much like the way they've split up the processes in Chrome itself. And importantly, each device runs inside its own mini jail. So they're using the same technologies as you use with containers to contain each bit of device emulation. So the idea of that is if they do get their device emulation wrong, and it's not unheard of to make a mistake doing device emulation, that there's a limit to the exploit surface that you can make use of. I'll just mention another feature. There's two block devices on here. The first one, VDA, is where all of the container runtimes is contained, or runs from, and it's a completely read-only device. So even if you manage to break out of the container, you can't actually physically write anything to that device. It's a signed read-only blob that comes as part of CHROMOS. So all the containers, all the user state is stored on the second hard drive. All right, the next example I want to talk about is KATA containers. So KATA containers are lightweight VMs, and they've got pretty heavy, excuse me, a heavy Docker integration. So the architecture looks a bit like this. So again, you have your host kernel. Containerd is a common abstracted way of managing container runtimes that both Docker and other container runtimes use. It starts the KATA shim. The KATA shim is responsible for launching the VM and then talking to the agent running inside the VM to launch its workload. So there's two things of note here. They have a particular build of a lightweight Linux kernel, so they don't use the host kernel, they build their own. And there's this little blob here called nemu. So the optimized kernel, again, as I mentioned earlier, you take out all the features that you don't need. A couple of things it can do. It's got a rootfs. It can run the rootfs either directly off an init.rd, so it doesn't need a disk, or off some sort of read-only NVDIM. And then there's nemu, which is a fork of the QEMU project. It actually stands for No Emulation Emu. So what they've done is they've cut out chunks of the unneeded emulation code from QEMU itself. Right. The third example architecture is gvisor. So some people might remember there was a talk about this at the beginning of the week. So again, we have our little VM. But this time, instead of running Linux, we're not even running Linux. The stub kernel here is a very small microkernel, and its only job is to take system calls from the application and then pass it through the VM exit to the host user space. And they have two binaries, Sentry, which deals with the system call emulation, and Gopher, which deals with all the file operations. And again, these binaries are contained on the host system, so they're limited in what they can do. Sentry will only pass a subset of the system calls through to the host kernel. It does quite a lot of the system call emulation directly in the user space binary. And it can't access any files, which is why all the file operations are pushed off to Gopher. Okay, so that's an example of some of the architectures. Just quickly go through some of the remaining work that needs to be done for QEMU. So first one is debloating QEMU. So on the way we currently build QEMU, we build all of the emulation support for all of the various different bits of hardware that we have. So nemu took the approach of cutting these chunks out and not compiling it that way. That's obviously not acceptable to upstream. There's a couple of things you can do. You can use the disabled TCG flag when you build it, and that will disable a chunk of the TCG emulation side, which is generally not used when you're using KVM. We've recently merged in support for the kconfig language. So this is the same as the kernel config language used for the kernel. So it's not the menu config tool, but just the descriptive definitions of what blobs of binary you need and what the relationship between those blobs are. So this is still very much a work in progress, but the idea is it would be easier to define a lightweight QEMU binary build without having to just cut out bits of the code. Finally, reaching feature parity with x86. So the big one that we came across this week was hot plug support. So there's patches on the lists for supporting hot plug in QEMU, but x86 being the first seems to get to dictate the choice of architecture. So there's choices to be made about how that gets implemented. So in summary, containers, they're popular. They're popular mainly because of the tooling and the ease of development they give developers, and they're pretty portable across any given Linux host. Virtual machines give you a more defined isolation by having a lower attack surface, because you basically can only attack the exit points that you give it. But there are performance trade-offs to be made, and you have to be careful in your decision about what virtual hardware you're going to have. VM exits are always going to be expensive. Container technologies aren't exclusive to containers, so they can add additional security to exploits against virtual machines as well. And in combination, you get the best of both worlds, and for security, it's always best to have defense in depth. So that brings me to the end. So if there's any questions, I will take them now. Do we have a microphone?
You mentioned the hot plug issues or to keep up with x86. Can you expand?
So, at the moment, we don't have hot plug for ARM. So there's no real hardware that allows you to plug in CPUs, and we've modeled something that works inside. Yeah, so plug it. So yes, you would boot up a one CPU low memory VM that consumes very little resources, but then when you want to run your container, you'd hot plug a bunch of CPUs and memory in, and that saves you having to go through the kernel boot, and you can get on with your task. But yes, for hot plugging in CPUs, we don't really have hot plug ARM CPUs. So x86 does this with ACPI, and the discussion is whether or not we have to do the same, even if we don't have hardware that actually works like that.
To carry on the subject. So it's not just ACPI. There's we need to define exactly what sort of resources we're going to hot plug. There's a bunch of CPU private blocks that come with the CPU, and we need to define how we model that, whether that happens in these interrupt control related bits get mapped dynamically, appear dynamically in the system, or whether they are pre-existing and only the CPU gets hot plugged physically or virtually. Clearly, the first approach is much more complicated than the latter.
Memory's a bit easier, isn't it?
Memory is definitely easier. It is removing memory that is pretty awkward, but hey, let's not go there.
Any other questions? All right, well, thank you very much.